right, let's go and get started. Take a look at our homework, page 398, numbers 13, 15, and 18 through 22. Students in here were at the academic fair last night, so they had homework passes. So they did not do all of it. They did answer a few of the questions at least, so we'll go to them for those. Number 13, what are the three components of a simple circuit? Audrey?
The three components of a simple circuit are the load, the conducting wires, and the battery.
Good, the load, the conducting wires, and the battery. Number 15, state Ohm's law and identify each variable. And this should have sounded kind of familiar to us. Kendall?
R equals V over I.
Okay, that's not usually the way we express it, but it's not wrong. V equals IR is usually how we express it. What do those three letters stand for? V is?
The voltage.
I is the? Help class? Current, and R is the resistance. Good. Number 18. How is equivalent resistance determined for resistances in series, Michael?
Equivalent resistance is determined in resistance in series by utilizing Ohm's law.
Yeah, in a way it leads there. Audrey, what did you have for number 18? Did not get that one? Kendall get that one? Mm-hmm. Okay, so I'll go ahead and answer the rest of the questions for those watching. Number 18, equivalent resistance for resistances in series is determined by simply adding the resistances, taking the sum of the individual resistances. Number 19, how do the current and voltage compare in series resistors? Well, in series resistors, the current is the same throughout, and the voltage varies by resistance. And letter C, how do the resistors' voltages compare with the voltage of the battery? The sum of the voltages used equals the voltage provided by the battery. Number 20, how is equivalent resistance determined for resistances in parallel? The equivalent resistance is calculated by finding the reciprocals of the individual resistances, taking the sum of those reciprocals, and then taking the reciprocal of that sum. So it's a lot of reciprocals, kind of like with the thin lens equation or the mirror equation. Number 21, how does equivalent resistance of a parallel combination compare with individual resistances? The equivalent resistance is always less than any one of the individual resistances. And number 22, how do the current and voltage compare in parallel resistors? For parallel resistors, the current varies by resistance, while the voltage is the same throughout all resistances. All right, so those would have been our answers for 13, 15, and 18 through 22. Let's review what we talked about yesterday, and today and in our next lesson, we'll get into some of what we talked about there in the homework. Started talking yesterday about a pathway for current. And what do we call a pathway for current, Michael?
Circuit.
A circuit. Now, in a circuit, I just realized we have old homework from the 8th graders up there. We'll take that down. For a circuit, right? A circuit is generally composed of a wire of some kind. And what is it that actually flows through a circuit, class? Electrons, delocalized electrons. And as these delocalized electrons move, they can either move all in one direction constantly, or they could go back and forth, oscillating in direction. Which one goes only in one direction throughout the circuit? DC. What does DC stand for, class? Direct current. And generally speaking, when we think of direct current circuits, we're thinking, class, of that which is powered by a battery. DC runs off a battery, generally speaking. All right, the ones that go back and forth, that is what type of circuit, class? AC, which stands for alternating current, and generally these are almost exclusively, AC is generated by some kind of AC generator. And these we will think of as things that are powered by doing what? Plugging them into the wall. If you plug it into the wall, that's running off AC, because what comes from the wall is powered by AC generators. Battery, that's your DC. For this class, what we're going to be dealing with, we're going to focus, class, strictly on DC circuits. They're easier to understand, and you could extrapolate some of the same truths out to the AC as well, but we're going to start with the DC, and that's what we'll focus on here. We said that the electrons, as they are flowing through the circuit, man, they are just flying through that circuit, right? Whizzing at incredibly high rates. No, they're not. No, they're moving very slowly. Do you remember the term for the slow movement of electrons through the circuit? drift velocity. And you remember, it's just really, really low, around less than a millimeter every second advance. So they move very slowly, and they move slowly because there's stuff in the way, so to speak. What do we call the impedance, if you will, to the progress of the electrons? That which hinders the flow, class? Resistance. Resistance is what hinders the flow. And we said in a wire, resistance is caused by three different things. What's one of those factors, Kendall?
The length.
The length of the wire. Now, if I make the wire longer, does that increase or decrease resistance? Increases. A longer wire, think of a longer hallway to have to navigate with kids in it, right? So instead of just one section of lockers to get through, there's two. Well, now imagine if we had like several sections of lockers you had to work your way through to get to class. That longer indicates more resistance. Again, not a perfect analogy, but I think it helps us to picture it. What's another factor, Audrey? The type of material, right? Those materials that have more delocalized electrons in them means more people, if you will, are all moving the same direction in the hallway. Fewer delocalized electrons means more people standing around talking while you're trying to get to class. So the type of material is going to affect the resistance. And finally,
Width.
the thickness, if you will, width, I'll take it, right? The thickness of the wire matters as well. Thicker wire would have more or less resistance. Less. Think of a wider hallway. It's going to be easier to navigate a wider hallway than a narrow one. Now, technically, for thickness, the better way to think of it, class, would be cross-sectional area. Cross-sectional area. Length, of course, is just length. And then for the material, we said every different material has its own natural inherent resistance that it creates. What was the term we used, represented by the Greek letter rho, to describe the effect of the material upon resistance? Anyone? Good, Audrey. Resistivity. And we said that resistance in a wire can be calculated based on these three factors. What was that equation that we had? Kendall?
Rho times length over cross-sectional area.
Good. Do we remember the SI unit for resistance from yesterday? Ohms. Represented by the Greek letter omega. And that would actually make some sense. The resistivity then has to give us the ohms while canceling other things. We said length of our circuit is going to have to be measured in centimeters. We're going to be dealing primarily with smaller circuits, so we're going to elect to go with centimeters for our length. Therefore, cross-sectional area will be in centimeters squared, and this is partly because the resistivities the book provides are given to us in what units, anyone? We want ohms, and we need to make these reconcile. Times centimeters. That gives us a second centimeter in the top to cancel with those down there. Again, this just comes from a table. That'll typically be given. Now, cross-sectional area. When I look at a piece of wiring, and there would never be, shouldn't be wiring quite this thick. If there were wiring, like thick wiring, when I look at it, I don't generally think, oh, that's the cross-sectional area. I usually think in terms of a diameter. Well, I've got to actually have cross-sectional area, though. How would I go from a circular cross-section, maybe a diameter or even a radius, to the actual area? Remember, the cross-sectional area would be pi r squared for a circular wire. What about ribbon wire, that rectangular cross-section? That's going to be simply length times width. Multiply the two dimensions times each other for that. From there, we talked about actually using resistance. And by the way, we did point out yesterday that, I don't know who we is, I'm schizophrenic now. I pointed out yesterday to you, we discussed that as long as the length is really small and you're actually using a conductor, it's going to be negligible resistance in the wire, right? Very, very low resistance. But I mean, there is some, and you could use it to your benefit. We talked about the ability to use an adjustable resistor to, for instance, allow more or less volume to play, to allow more or less light to shine. What do we call that adjustable resistor? We can control the resistance. Rheostat. Okay, so think of when you're controlling the temperature in your home, thermostat, right? Rheostat. So think of the stat part. You're controlling something, controlling resistance. Restat. We throw in an O for good measure and an extra H for the spelling. A rheostat. Okay, so I don't know if that'll help you remember it or not. Rheostat, that adjustable resistance. We talked about this flow of delocalized electrons throughout the circuit. We said again that flow of electrons, that flow of charge, class is called current. And we said that current is simply the flow of the electrons. The electrons are already there. They just need a little push to get them moving. What do we call that push that drives the electrons through the circuit? Voltage. Technically, it's electrical potential difference, the difference between the positive and negative charges. Okay, the bigger the difference, the greater the push that pushes electrons through. But it's called voltage. And as we go through the unit, if we'll think about voltage as that electrical force or pressure that pushes electrons through a circuit, that'll help us. We had an equation to find voltage, and it was actually Ohm's law from the homework. What was that, class? V equals IR, where the V is the voltage. What's the unit for voltage? Volts. I represents current. What's the SI unit of current? Ampere or amp. And then the resistance, we already said, class is measured in ohms. So it was our second equation that we needed for this section. We said if you could decrease the resistance, you wouldn't need as much voltage. Or if you decrease resistance and you kept the voltage the same, you get a lot more current to flow. And we could decrease resistance in a wire or in a conductor if we could lower its temperature down toward absolute zero. That would decrease resistance dramatically, and that would turn any conducting material, any metal, into a superconductor. So you can make a conductor into a superconductor simply by lowering its temperature. If, on the other hand, we wanted high temperature, we would want to actually increase resistance and increase the current flow by using a whole lot of voltage. If you take a whole lot of voltage to ram a whole lot of current through a whole lot of resistance, it will produce heat. The book mentions different heating coils are oftentimes coated in high resistance materials to try to increase the production of heat in things like ovens and drying elements and things like that. All right, let's take a look at the next part of the homework, which you guys happened to not do, so we'll go over it, though, together still. The problems 1 and 2 from page 398. Read problem 1 for us, if you would, Michael.
The heater wire in a small stove is made of iron ribbon wire of 0.01 centimeters by 0.05 centimeters in a rectangular cross-section and 2 meters long. Calculate its resistance.
All right, so we have this wire that runs throughout the stove. It's 2 meters long in total, and it's a ribbon wire. It's made of iron, and it's 0.01 centimeters by 0.05 centimeters. Well, that's your length times width. That's your cross-sectional area. So if you had done it last night, you would have already calculated that. But what is it? It's okay. You got the homework passes, so no problem at all. But what do we get for that cross-sectional area? 0.01 times 0.05? 0.0005, right? We did that in our head, couldn't we? 5 times 1, 5, 4 decimal places. And a centimeters times centimeters? Centimeters squared. There's our cross-sectional area. The length, it said, was, but I don't want meters for some weird reason. I want centimeters, so 200 is the length. And it's made of iron. Well, iron has a different resistivity than other materials. Flip back several pages, back to page 382. And what is iron's resistivity? And that's your ohms times centimeters. That's a terrible ohm. Ohms times centimeters is somewhat better. All right, so at your seats, plug it into the calculator. And how much resistance do we get in this wire? 3.88 ohms of resistance. It looks like we only have 1 sig fig, so let's say we have roughly 4 ohms. That's a pretty significant amount of resistance, 4 ohms of resistance, but it makes sense. The purpose of the wire is to heat, right? So we want resistance in our wire. Questions on number 1? Again, we didn't do it for homework. Do we feel like we would have gotten it if we'd done it? Feel like we understand it? Okay, read number 2 for us if you would, Kendall.
A fine platinum wire, 0.1 millimeters in diameter and 50 centimeters long, is used as the sensitive element in the electrical resistance thermometer.
All right. Now this time it mentions a diameter. If it mentions a diameter class, that means it must have what shape? Circular cross section. So now when we find that cross-sectional area class, we're going to have to go with the pi r squared. Now it says the diameter was 1 millimeter or 0.1 millimeter?
0.1.
0.1 millimeter. Very, very small. Okay? But if that's the diameter, what's the radius? 0.05 millimeters. But I don't want millimeters, I want centimeters. So what would that be? 0.005, right? You're going from an E negative 3 to an E negative 2. That means you're going up one, she up and left. Go to the left one. And there's our radius. So this time, as we plug in the numbers, we're going to have pi times the 0.005 squared. What was the length again, Kendall?
50 centimeters.
50 centimeters, already in centimeters, that's nice. And it said it's made of what material?
Platinum.
So back to page 382, what is platinum's resistivity, anyone?
1.1
All right, and so plug that into the calculator now. Be careful as you do so. And how much resistance this time? Ooh,
7.0.
I got a 7.00 blah blah blah. Is it 1 sig fig again? It is 1 sig fig again, so just a nice easy 7 ohms of resistance. Michael's re-entering it. Ladies, you both got it. And waiting on confirm. No, not getting it. Did you use 1.1 E negative 5?
I have 1.9.
Oh, okay. All right. That, yeah, that would probably give you a 12. Re-enter it with the 1.1. Let's see if you got it.
Yeah, but my decimals off.
All right, let me check real quick. It's got the, oh, yeah, parentheses around that. There we go. Okay, he figured it out. All right, and that's why I like to do divided by this, and then I also divide again by this, by the next thing, just because I don't like to mess with parentheses. But it's not wrong to do it that way. All right, questions on what we talked about yesterday, introduction to circuits. All right, let's talk now about parts of a simple DC circuit. Next thing you need to know is parts of a simple DC circuit. It's actually from your first homework question, question number 13, parts. Of a simple DC circuit. First thing you have to have in order to have a circuit, again, a piece of wire is not a circuit because there's nothing causing the free electrons, those delocalized electrons, to move. Something has to push them. Does that make sense? There has to be an impetus, so to speak. So the first part of a DC circuit is you must have a source of current. Now again, by source of current, I don't mean a source of electrons. I mean a source of voltage. So source of current, if you would put this after it, this provides the voltage, which we already understand to mean provides the push. The source of current provides the voltage. This is your battery. The source of current is your battery. That provides the voltage. In a DC circuit, you'll see this notation. You can tell there's a battery when you see two parallel lines, one long, one short. That's the symbol in the network schematic for battery. The long line is your positive terminal, and the short line is your negative terminal. So when you see that notation, that's my battery. The next thing you have to have is the way for the current to actually flow. So we do need that wire we talked about. We just need the battery to start pushing the current through. So the next thing we need are conductors. Conductors. These provide the path. For the delocalized electrons. So you need conductors. They provide the path for the delocalized electrons. In plain English, these are the wires. So you got a battery, you got wires. Source of current, that provides the voltage. The conductors, that provides the path. However, as I said before, if all you've got is a battery with wires connected to the ends, do you really have a circuit? I mean, yes, current is moving, but it's not doing anything, right? It's doing nobody any good. All it's doing is running down your battery and potentially causing fires. So you need then something that will actually use the current, something that benefits from the current. We call these things the loads. I'm going to put the S in parentheses because you don't have to have more than one. You could just have a single load, but the load or the loads, these are the things that use the current. This is the purpose of the circuit in the first place. These also, if you will, can be referred to as resistances. Because when current is used, inherently resistance is present. How does a light bulb light up? It provides resistance, and the glow of the resistance produces light. How does a fan motor turn? It uses that current, right? So the thing that uses the current will inherently cause resistance to be present. We're going to represent resistances with a squiggle line like that. You may also sometimes see it enclosed in a circle. Now, technically, there is a difference. Technically, this means a resistor. This means an actual load. We'll typically, because I'm lazy, we'll go with the first one because I don't like drawing circles. So I'll usually just use resistor rather than load notation in this class, just because I'm too lazy to put the circles around them. The loads have resistance anyway. Resistor. Maybe it's a light bulb, maybe it's something else. But technically in the schematic, there is a difference. In this class, we'll just go with the first one. As far as the conductors, there's just lines showing where the wires would be. All right, now one other thing to understand as we go to drawing circuits and thinking through circuits here in a moment is technically what is moving in the circuit class? Electrons. Electrons would move from an area of high negative concentration to low negative concentration, correct? Electrons then would move from where there is negative, the negative terminal, around to the positive terminal, technically. But when electricity was first being researched by Benjamin Franklin, he thought that electricity was a flow of positive charge. He was just that upbeat, happy individual. Wasn't a realist. Realism, life is negative. Just kidding. But Ben Franklin said that it flows from the positive to the negative. Since he laid all that groundwork and we had a whole lot of things already documented with his research, rather than go back and undo all of that, we've just all kind of agreed we're going to keep drawing and imagining that things flow from positive to negative. We call this conventional current. That which is conventional is that which has always been done, right? Something that's unconventional is new and crazy. Like when Donald Trump ran for president, here's a billionaire businessman, hotel and casino owner. What's he doing running for president? He's supposed to fire people on his TV show. Who is this guy? He was unconventional, right? His approach to a lot of things was unconventional. And at the same time, I would argue he got a whole lot of good stuff done. But it was unconventional. It wasn't normal, right? What we have right now, President Biden, much more conventional. He's been in politics for 50 years. Like most politicians, he's never really done anything, all right, except make money for himself and his family. Unfortunately, there's too many. That's conventional, right? It's always been done. A convention, a place where a whole lot of people get together that already think the same way, and they excite themselves about what they're talking about because they all agree already. It's conventional, okay? Conventional current, it flows from the positive to the negative. It may defy realism a little bit, but it's what we're going to go with. Conventional current. So in our schematics, we're going to assume that the current comes from the positive longer line terminal and goes around to the negative end, even though that's not what actually happens. All right, so that's how we're going to draw our schematics. A simple circuit then might look something like this. If you want to draw yourself an example, you'll have the two lines, one long, one short. Current will flow. We generally draw our lines at right angles to each other, even though realistically we know wires don't always form nice hard right angles. They get curved and bent and twisted around stuff. But this is a basic circuit, what it would look like. Here's your battery. Current is going to flow around this way, through the load or the resistance, and it's going to go back to the battery. So that's what a very basic circuit might look like. Let's suppose I have a 6-volt battery. Now you know what the little AA, AAA batteries, have you ever looked at the side to see how much voltage each one gives off? How much? 1.5 volts. So a typical little AA, AAA, any type of, technically they used to call them cells. Now they're like, everybody calls them batteries now, let's just officially call them batteries. But anyway, it would take 4 of those to get 6 volts. In fact, you know what a 9 volt battery is, right? Like what Adam used for his project at the academic fair last night. If you were to break one of those open carefully, you would find 6 little, they're smaller than AAAs, but they're basically like AAA batteries, 6 of them inside there, all connected. And that provides 9 volts, 6 times 1.5. So anyway, 6 volts is basically 4 AA's all used together. All right, and they provide current. Let's suppose this particular resistance is 4 ohms of resistance. Well, we already have an equation that shows the relationship between voltage, resistance, and current. What was that equation from yesterday, class? V equals IR. Now, we originally put it on the board as R equals V over I, and then we showed I equals V over R, and then we said V equals IR, and we said that's easier to memorize. It is, and it's called Ohm's law. Ohm's law. The relationship between voltage, current, and resistance. And we can use Ohm's law to solve a circuit for its missing parts. If we know the voltage, we know the resistance, and I want the current, how would I get I by itself? Divide the R. So we're going to memorize V equals IR, but we're going to be able to construct or extrapolate I equals V over R. Well, if we got 6 volts and we got 4 ohms, 6 divided by 4, class, gives us 1.5, what do we measure current in? Amps. 1.5 amperes or 1.5 amps of current. So basically, if we have 6 volts, that's enough force or pressure to push 1.5 amps of current through the network, or through the circuit rather, across the load and back again. Now, you realize we are assuming no resistance in the wire. And as we said yesterday, we're going to, for the sake of our sanity, because realistically resistance in a wire like this is less than 1/100th of an ohm anyway. It doesn't mess with the math much, so we're choosing to ignore the resistance in the wire even though we know it's present. Questions on Ohm's law, questions on what a basic circuit might look like. All right, turn to page 385. Page 385, I feel like I'm losing my voice. And read example 25.2 for us, Audrey. Give my voice a rest.
A battery is connected to a single unknown resistance. What is the resistance if I is 1.5 V and R is 0.022 A?
Okay, instead of saying A and V, let's actually use the words that they stand for because it'll help us remember. What is the resistance if V is?
1.5 volts.
And I is?
Current is 0.022 amperes.
There we go, excellent. All right, so it says, what is the resistance? And they give us the voltage and they give us the current. How do I get R by itself, class? Divide the I. So R equals V over I. So we plug like they did. We plug in the voltage, 1.5 volts. And we have the resistance, which is, or the current, excuse me, which is 0.022 amps. And that will tell us how much resistance we must have. And when you divide, it comes to approximately, the book says 68 ohms. What's the actual number?
68.1818.
181818, rounded 68 ohms of resistance. That's a whole lot of resistance. All right, questions on that? All right, turn to page 398. Turn back to page 398 then. And we'll use Ohm's law to do problems 3 and 4. Page 398, use Ohm's law to do problems 3 and 4. Go ahead and read problem number 3 for us, if you would, Michael.
A 3-volt battery is used in a flashlight having a bulb with a resistance of 25 ohms. Find the current when the light is turned on.
All right, obviously there's no current when the light's turned off, right? We understand what a switch does. By the way, in the schematic, you might see something like this notation. This would indicate the presence of a switch. When the switch is closed, the current flows through. When the switch is open, it doesn't. But anyway, 3 volts. So again, that would be 2 little double A's, for instance. And a resistance of 25 ohms. That's a lot of resistance for this bulb. We use the equation class, V equals IR, but I'm solving for the I, so Michael, I adjust it to say
I equals V over R.
and we divide the V, the 3 volts, by the R, which was the 25 ohms. What do you get for your answer?
0.12 amps.
0.12 amps. Very little current goes through. Do we get 0.12 amps, ladies? All right, number 4. Go and read that one for us, Kendall.
A 12-volt storage battery is used in a truck. If 4.8 amps is supplied to the circuit, what is the resistance of the circuit?
All right, so a 12 volts, by the way, that is a typical automobile battery, somewhere between 12 and 13 volts. So if you're ever curious how your battery doing, you can take your voltmeter, right, touch the connectors to the terminals, right, and have somebody crank up the engine and see what your voltage does. I had to do that recently because my car was starting to have a few little issues starting. Not bad, but makes me nervous. I don't want to be stuck out there somewhere. And we ran the test, and sure enough, like when it started, it dropped to 6 volts reading. I'm like, yeah, that's not supposed to be the case. So I went and got a new battery. I found out batteries went up. I used to be able to get a battery for around 100, 120 bucks. Yeah, it's about 180. That's for the cheap one. Like they were like 300 or 400 for some of the nice ones. I'm like, what happened? Biden happened. Just kidding. Inflation happened. But anyway, so sorry. We're finding the resistance. Okay, so we start with the equation class. V equals IR, right? But since we're finding resistance, we modify it, Kendall, to get
R equals V over R.
and we're going to divide the 12 volts by the 4.8 amps. And what do you get for your answer?
2.5.
Resistance measured in?
Goodness.
Not but you're close.
Oh,
Not
ohms.
Ohms, there we go. 2.5 ohms is correct. All right, questions on that? Ohms. Questions? All right, feel good about Ohm's law. Easy equation to use, yes? Easier, frankly, than even the resistance in a wire equation. All right, let's then talk about this type of circuit called a series circuit. Next thing in your notes, a series circuit. A series circuit is one in which current goes through each load in succession. A series circuit is one in which current goes through each load in succession. Current goes through each load in succession. On a schematic, it might look something like this. The current comes out of the battery and it goes through a load or a resistance. After passing through that load or resistance, it might go through another one. And then it might go through another one. And then maybe it comes back to the battery. So the current is going to flow out from the battery, being pushed from the battery across a resistance because there's no other alternative. That's the key. There's no options. It's like having one hallway in the whole building. Well, we do. We have 3 stairwells at least, okay? 3 ways to get downstairs, but it's still one long hallway. Well, and downstairs there's a couple side, whatever, okay? But imagine just one long hallway. Everybody has to use it. It's kind of what we have here, like I said. Well, imagine if you had several hallways. That would give you more options, right? There's not options here. There's only one path. The current has to go across this resistance before it then must go across that resistance, before it then must go across that resistance, and finally it returns to the battery. Does that make sense? That's a series circuit. Well, we understand, let's just say, again, we've got a 6-volt battery for sake of illustration. Let's suppose the first resistance is a 2 ohm resistance or a 2 ohm load. The next load might use only 1 ohm of resistance. Perhaps the next one has 3 ohms of resistance. What we're going to want to do then is to determine what is the equivalent resistance in our series circuit. And it's very straightforward. Since all the resistances are encountered one at a time, it's like you play video games. Okay, the little video game guy, you know, I haven't played video games in forever, so this might not be the way to do it anymore. But back when I was younger, you would have a certain amount of life, and as you encountered hardship, you would lose life or level until eventually if you ran out of life, you were done, okay? Well, imagine you encounter hardship, you lose a little bit of life, and then you lose a little bit more, you lose a little bit more. It kind of just keeps adding up. That's kind of what's going on with the current. There's this push from the voltage, and it pushes across the first resistance, and some of that resistance uses up voltage. And then it encounters more resistance, and it just keeps using up voltage. Equivalent resistance, or total resistance as it's sometimes called, equivalent resistance is simply the sum of all the individual resistances. It's an equation to know, but it's a stupid easy one. You just add them up. So here, if I've got 2 ohms, then 1 ohm, then 3 ohms, what is the equivalent resistance for this particular series circuit, class? 6 ohms. So the battery is putting out 6 volts of push, so to speak, and it's going to encounter in the entire circuit, all collectively, 6 ohms of resistance. The question then becomes, how much current can go through this circuit, right? The more resistance you add in, it makes sense, less current, right? If the voltage stays the same and you increase resistance, that's less current that can get through. Well, using the equation V equals IR, solving for the I class, how much current will go through 6 ohms if it's pushed by 6 volts? 1 amp. Don't you wish all of your problems solved that easily? Okay, for sake of illustration, we'll use some nice easy numbers here. 1 amp goes through. Now, that current is 1 ampere's worth of electrons being pushed by the battery. 1 ampere's worth goes here and crosses the 2 ohm resistance. That same 1 amp comes here and goes across the 1 ohm resistance. That same 1 amp goes here across the 3 ohm resistance, and that same 1 amp comes back to the battery for another boost. Does that make sense? There's no other options. What that means is if I know the resistance and the current, I can then find how much of the voltage gets used up right here. 1 amp through 2 ohms uses how many volts? V equals IR, 2 volts. 1 amp goes across 1 ohm. How many volts? 1 volt. 1 amp through 3 ohms. How many volts? 3 volts. All the voltage has been used now. Does that make sense? Now what you see is you see a voltage drop. If you want to think of it again, we talked about electrical potential difference. The electrical potential difference between the terminals of the battery is 6 volts. But once the current flows across here, we're down to 4 volts of electrical potential difference, 3 volts of electrical potential difference, and now that we've gone across here, we're back to neutral. It's been used. I think of this. There was my cousin had a really cool Hot Wheels racetrack, and there were these little foam rollers that would spin like this, and they could just fit the Hot Wheels car in between the foam rollers. If they were still, it would stick just the tiniest bit, a little bit of friction, but it would shoot the car around the track. It would go really, really fast around the track, and it would start to slow down, slow down, slow down, slow down, slow down. And if you designed the track just right, it would just be slowing completely when it reached those foam rollers again. And get another boost and shoot around the track. Kind of what we've got going here. We've got this boost of push for the current to go through. And it's like it encounters a loop on the track or something, and it loses a little bit. And it comes across here and it loses a little bit of voltage. Not current, current's still the same. Loses a little bit more just in time to get back to the battery and get another boost to go around this curved circuit again. And that push just keeps replenishing and keeps the current flowing through. Now, what I want you to notice here is, it's the same current every time. So in a series circuit, we need to know that the current is constant. We need to know that the current is constant at every resistance, because there's nowhere else for it to go. But what you notice is what is different at every resistance. Well, obviously the resistance is, and because of it, the voltage varies at each resistance. Do you see that? So we need to know that for the series circuit, current is constant and voltage varies. By the way, voltage is sometimes referred to as the IR drop. There's a drop in electrical potential difference. Or V is IR, so IR drop. There's an IR drop at each resistance. Now the nice thing about this is if you think English class, listen, for a series circuit, current is constant and voltage varies. Makes it easy to remember. You see what we did there with the alliteration? Okay. That's going to help you remember that, I hope, as we go forward. All right. We don't have time to look at that next example problem. We'll pick this up in our next lesson. No homework this evening. Have a wonderful rest of your day. And when the bell rings, you'll be dismissed.